Our next speaker is even more local. So, Jinzu Yen from Peking University. Then I have to see if I can get out of trying to pronounce pleiotropy. I can never. So it's Mendelian randomization, and then looking at that nasty assumption, which we all know is very, very critical, but hard to pronounce. So, floor is yours. That was a joke, but pleiotropy, I think it's awfully difficult to pronounce, but I have looked a lot at robustness results towards it.
Thank you, Sis, for the introduction. I'm very happy here to introduce my recent work. This is a joint work with my PhD student in talk. So my talk is on Mendelian randomization. So it is for binary outcomes with pleiotropy-robust. So this word pleiotropy is not a statistical word. So it is from genetics. So okay. In the morning, Professor Binet have already talked on the Mendelian randomization application for the causal relationship between alcohol and the health status. So here, first I will introduce this method formally, and then I will propose a new method for non-standard setup. So usually for the continuous outcome, people use a linear model to estimate the causal effect, and it is very easy to use the instrumental variables. But if you have the binary outcome, the two-stage estimator is not consistent. So that is the problem. I will introduce the problem later, and then I will use some simulations and real data analysis to show that our models work for this kind of setup. Okay, this is Mendelian randomization. Basically, Mendelian randomization is causal estimation method based on the instrumental variable. So it is a statistical technique that uses genetic variants, usually the SNPs, as instrumental variable to estimate or infer the causality between different traits or between different diseases. So in the morning, we have already see that Professor Binet used SNP, used two SNPs as the instrumental variables to estimate the causal effect between alcohol and the health status. So this is a traditional model for the instrumental variable estimation. So people are interested in the causal relationship between the exposure X and Y. And because there are some unobserved confounder U, so you cannot estimate the causal effect between X and Y. To get a consistent estimator, so people can use the instrumental variable here. This is G. And to make the instrumental valid, it has to satisfy three assumptions. The first is that the G should be correlated with X. And this is this could be verified from data. In the morning, you'll see that the two SNPs is high correlated with the alcohol assumption, right? But the other two assumptions are usually not cannot be verified. So it assumes that this instrumental variable, say the SNPs, is independent with the confounder. So usually this assumption cannot be verified because the confounder is not observable. Because you do not know what the confounders are, and even if you know what the confounder is, but you cannot observe the confounder, so you do not know if the instrumental variable is correlated or independent with the confounder. But some by logical process can imagine what the U is, and the this they believe that the some SNPs is independent with a confounder. So if you have that belief, then you can use this. So there is another assumption says that the G is not a direction cause of Y. It means that all of the causation from G to Y just mediated by this X. So this assumption is also not it can also cannot be verified. So this is a big issue in the Mendelian randomization. And if the three conditions hold, then people could use the ratio estimator or word estimator to estimate this causal effect. So by these two parameters, bit height gy and bit height xg. So here, bit yg height is the linear coefficient that you regress this y on this g and get a linear coefficient. And also here, bit xg is that you run linear regression. You regress this x on the g and get a linear coefficient. So the ratio of the two linear coefficients are the causal effects. So this is a standard instrumental variable instrumental variable estimator for the causal effect. And now you see that you have these three assumptions, and also you need a linear model. So what if you do not have a linear model, especially if y is a binary outcome? So what can we do? This is some projective that we have already done in our group. We use a Mendelian randomization to analyze some causal relationships between a few traits. So I will skip this slide. Now I'd like to introduce two main problems about the traditional Mendelian randomization. The first thing is that if y is binary outcome, then you cannot use a linear model to get the estimator of the causal effect. Especially in the literature, people usually use a logistic regression to estimate the OR. So they still use the two-stage estimator. So for the first stage, you regress the y on the instrumental variable, but the model is a logistic regression model, not the linear model anymore. So if you do it that way, we can prove that estimator, the ratio estimator, is not consistent. So because it's not consistent, so we cannot interpret that bit as a causal parameter. And here is an example. If we set the true parameter of the OR here, and we use the MR ratio estimator as shown in the red dots, and you can see that the bias, there are a huge bias. And this is for the continuous outcome, and this is for the binary outcome. No, continuous exposure and the binary exposure. So another thing for logistic regression is that when you give different covariates, so when you adjust the different covariates, you get different estimator for this OR. So it is very hard for people to interpret this parameter as a causal parameter. So another problem about the MR is the pleiotropy thing. For the pleiotropy, I just said pleiotropy is it's not statistical word. So pleiotropy means that if this assumption does not hold, we say that there is a pleiotropy. And also, if this assumption does not hold, you also have a pleiotropy effect. So for this pleiotropy effect, it is called uncorrelated pleiotropy effect. And for this one, if this assumption does not hold, you have a correlated pleiotropy effect. So the pleiotropy effect will make the estimator of the causal effect very difficult. And in a single SNP, like here, if the two assumptions do not hold, then the causal estimator, the causal effect is not identifiable. So then that is why in the morning when Professor Burnett tried to get the causal estimator, he selected two SNPs, and Professor Zhou argued if the two SNPs satisfy the two conditions or not. So in the Mendelian randomization, usually you have too many SNPs. You have so many SNPs that if you use any one of them as an instrumental variable, you will have an estimator of the causal effect. So you have a lot of estimators, and these estimators will tell you something about if the SNPs are valid instrumental variable or not. So in the Mendelian randomization, if the pleiotropy effect exists, I mean the two assumptions between the instrumental variable and the confounder and the direct causal effect, if they exist, then you can still estimate the causal effects under few assumptions. Okay, now we are trying to propose a method called MR problem to surmount both problems. The first is about the inconsistency, and the second is about the horizontal pleiotropy. So this is a basic setting. Now we set the SNP G as a categorical variable. It is not a continuous variable anymore, because in the traditional MR analysis, people use a linear model. So they treat all of the variables are continuous and they use a linear model. Here we treat the SNP as a categorical variable. It has 3 levels. And we now use 2 dummy variable to denote it. So here G1 and G2, it seems it has 2 instrumental variables, but it is not. It is just a 1 instrumental variable G, and it has, because it is a 3-valued categorical variable, so we use the 2 dummy variable to represent this instrumental variable. And here, so for each of this model, we just use 1 SNP. We use 1 SNP at a time. So we use a lot of SNPs, but for each time we just use 1 SNP to get the estimator of the causal effect. After we have a lot of causal estimator, then we can put them together into a joint model and then estimate the causal effect. So then we use a log linear model. So we do not use logistic regression anymore because, as I have already introduced, the logistic regression model cannot give you a causal interpretation of the parameter OR, and it has some problems because you cannot get a consistent estimator in the logistic regression model. So here we now use the log linear model. So this is a big difference between our model with the traditional MR model. So here, the relationship between X and the log P is a linear relationship, and then this is a categorical dummy variable, G1 and G2. They denote the 2 levels of this 3-valued category. And okay, this is a basic model. And here, this H is the horizontal pleiotropy, and U is just the noise variable. Okay, now after we have this model, then how can we estimate this beta? Of course, you can use maximum likelihood as estimator to estimate them, because usually we have a lot of SNPs. So for each time we have an estimation of this H, it depends on the SNP that you use. So we have a lot of SNPs, then we have a lot of the estimate of this H. So if we assume some prior knowledge on this H, then we could have the random effect model. But if you want to use a fixed effect, it's also okay. And also we have two subtypes depends on the exposure is continuous or binary binary. So first, let's see the continuous exposure. So X is a continuous, Y is a binary variable, and G is a sniff. And here we do not assume the valid instrumental variable. So it means that this relationship between G and U can exist, and also the connection between G and Y can also exist. So here it is called correlated pleiotropy, and this is the blue part is called uncorrelated pleiotropy. Then we decompose this pleiotropy as three parts. This part is it has no pleiotropy. It means that it is a valid instrumental variable. And here this part means that only the uncorrelated pleiotropy exists. And here it means the red part means that both correlated and uncorrelated pleiotropy exist. So this is a model. So after we have this model and after we have the data, then we can try to estimate of the parameters. So when we estimate the parameters, we first get the marginal estimator of this M. This is a marginal estimator of the log linear model. You regress this Y just on the instrumental variable. You have this M, so we can have the joint distribution of this estimator, and then we use a maximum likelihood estimator to estimate this beta. Okay, this is an example of that we use a lot of snips for each dot. Means that we use one snip to get the estimate of the parameters. And clearly we see that we can divide these snips into three categories. The black one means that there is no no horizontal pleiotropy, and this dot line means that we have the uncorrelated horizontal pleiotropy, and the blue line means that we have the correlated pleiotropy. Okay, so if you could divide the snip into the different parts, then you can only use the part that it does not have any pleiotropy effect. It means that for those snips, you can treat them as the valid instrumental variable and then estimate the causal effect. And also you can use all of these snips together to have a joint estimate of this parameter beta. Okay, for binary exposure, again, we see if X is binary, we still cannot use the logistic regression model, because the logistic regression model, if you cannot see the confounder U, then you cannot get a consistent estimator of the parameters. So we still use the log linear model. Log linear model can give you consistent estimators. It's very similar to the continuous ones. After you have this exposure model together with the outcome model, then we could get have the maximum likelihood estimate of the parameters. Okay, the first part is about the continuous. Is about the random effect model. So if we really want to estimate the fixed parameters about the pleiotropy, we can treat the parameters H as a fixed parameter and try to estimate them. There is no much difference. But the thing that if you want to estimate this parameter, you have to have some assumptions like the we call the this proportional assumption. It means that the the parameter K and parameter H. K is the effect of the instrumental to the exposure. H is the effect of the instrumental variable to the outcome. So the two parameters cannot be proportional. If they are proportional, then the causal estimator is not identifiable. So if if they are proportional, then we can try to use because some SNP can be used to for some SNP, the two parameters are not proportional, but for some SNPs the two parameters are proportional. Then we can use some SNP to get an estimate of this beta, and then try to test if this H1 and H2 is 0 or not. If both of them are 0, then it means that the SNP is a valid instrumental variable, and then we can use the standard instrumental variable method to get the estimation of this beta again. Okay, so this is procedure that we are trying to analyze the GWAS data. So now you have the SNPs, and we converted the SNPs to two dummy variable. Okay, and then we can use a random effect model or fixed effect model. We either is okay. So this is a random effect model, and you have to give some prior on the pleiotropy effect, and this is a fixed effect model. And also you can just ignore the assumptions. Try to use each SNP as an instrumental variable and just estimate the causal effect, and then try to do the meta-analysis on the estimators. Okay, here are some simulations. We compared a lot of methods, and the basic information is that here this method gives you the smallest bias, and also gives you the good coverage. And this method is called randomized effect randomized effect model. Okay, we also did a lot of real data analysis, and from this research, we know that some traits are, and for some pair of traits are causal related, and some pairs of traits are not causal related. And here we have 31 pair of causal relationships, and we have 22 non-causal pairs of non-causal pairs of relationships. And we see that for our model here, we have a lot of this. We detect a lot of the causal relationships, and we did not report any of the non-causal ones. So this means that our method is powerful. And here is a report of the comparison. So after the experiments, we see that the simple random MR method usually have relative biases from negative 103 to 178, and usually the OR estimator usually give us very relative smaller causal effect. And also we see that in the trait pairs, about 26% of them were detected to have significant correlated pleiotropy. So if you ignore the correlated pleiotropy, you have biased estimator. And here we see that the traditional OR gave you a very small causal effects, and our model will give a relative bigger causal effect. Okay, this is my talk. Thanks.
Thank you. We have time for a single quick question.
Yeah, thanks, Jinju, for the nice talk. So I want to ask, if I understand correctly, so you did the sleeps separately, right?
Yeah.
Is there any benefit of putting them together? like to get to have a high dimensional like instrument variable?
Okay, this is a very good question. So the problem to have a multi-variable instrumental variable is that here you have a lot of SNPs, and you even do not know which one is a valid instrumental variable. So if you know that each one of them is a valid instrumental variable, then I think it is better you put them together, because you will have a strong instrumental variable. Because we know that if an instrumental variable is very weak, I mean that it has a very small correlation between the instrumental variable and the exposure, then the estimate of the causal effect is biased, right? But if you want to put them together, you at least have to know that they are valid instrumental variable. But if they are not, then these single ones will detect which ones are proper, which ones are not.